kind of explore why we would want to use it, where it comes from, how it links to our definition of the derivative in particular. So remember, the definition of the derivative is this. The limit as h goes to 0 of the difference quotient f of x plus h minus f of x divided by h. Let's just apply that rule down here, and we'll apply the power rule and make sure that they agree. And then we're going to get sick of it, and we're just going to notice that they agree. At the end, I'll try to just give you an outline of the proof of the power rule if you are interested. Okay, so according to this, again, I'm using different notation there. That d dx means to take the derivative, but let's just assume the function f of x is x. So therefore, the derivative, according to our definition above, would be f of x plus h, which would be x. So our function is just f of x equals x. So f of x plus h is just x plus h minus f of x, which is x, divided by h. And we get the limit as h goes to 0 of the x's cancel. You get h over h. So that's clearly a 1. If we use the power rule, on the other hand, we want to think of this as x to the 1. So using the power rule, according to this, we would say we bring down that exponent, right? The 1. We diminish the power by 1 according to the rule. X to the 0 is always 1, so this is 1 times 1, which is 1. And that agrees. I didn't write my final answer over there, did I? And that agrees with what we got over here. The other way you can think of this is graphically. The graph of y equals f of x equals x is just a diagonal line through the origin with a slope of 1. So the derivative would be 1 everywhere because the slopes would be 1 everywhere. Let's do one more. Let's think of this as f of x. F of x equals x squared. So therefore, the derivative by the definition would look like this. So f of x plus h would be x plus h squared minus f of x, which is x squared divided by h. Let's deal with the difference quotient first. So the difference quotient will reduce to x squared plus 2xh plus h squared minus x squared divided by h. We see conveniently that cancels with that. And therefore, we can now write this as, here I'm going to factor out an h from both terms, and I get 2x plus h divided by h. Those cancel, and we get 2x plus h. So this is just going to be the limit as h goes to 0 of 2x plus h, and that equals 2x. That was using the limit definition. Let's try now using the power rule. So according to the power rule here, we bring down the exponent and diminish the power by 1. So by the power rule, f prime of x would be, or the derivative of x squared would be 2x to the 1, which of course is 2x. Okay, and that agrees, as we noted, with what we did, or what we got when we did it out the long way. So at this point, let's get away from that definition. It's getting too tedious because you have to keep expanding that binomial there, or the that first term. It was a binomial at that in the last example. Let's just use the power rule here. So we take the 3 here, we put it in front, we diminish the power, we get 3x squared. So it's easy to apply, and it's a lot less work. So let me just finish for those who are interested what the proof would look like. The proof is going to involve this x plus h to the n power. So if we're thinking of if the actual problem is like, f of x equals x to the n, we want to show that the derivative is n x to the n minus 1. The way you do that is you need to understand the x plus h to the n can be expressed in terms of the binomial theorem. And what that means is if you were to write out the terms, it would look like this. X to the n plus So then the powers go down, x to the n minus 1. They go down on the x's, they go up on the h's. And then the coefficient would be n choose 1. Okay, again, if you haven't seen this before, it's not the biggest deal. You don't really need to know it for AP Calc, but I'm just kind of throwing it in. The next term would be n choose 2 x to the n minus 2 times h squared. So the h exponents keep increasing, and the x exponents keep decreasing, but eventually the last term would be h to the n, and the coefficient would be a 1. The reason that's important is because in order to show this, you would, right, using our x plus h definition, you would get it set up like this. So f of x plus h would be x plus h to the n minus x to the n divided by h. And the idea here now is, rather than write it all out, just notice that this, right, would substitute in for that. And then you immediately get a cancellation that you want. That goes away, or that cancels with that. So then what? Again, remember, the goal is to get that h to cancel in the bottom. Well, if you factor out an h from this expression above, right, so the x to the n is gone. If you factor out, let's see if I have a little bit more room here. If you factor out the an h, because every term here has at least one h to give, you get this. The other thing I should know is that n choose 1 is the same as n. You need that fact. So you get h times n x to the n minus 1. And then I'm not even going to write the rest of the terms, because every single term to the right of this plus sign here highlighted has an h in it, even when you factor 1 out, because the second term had 2. And all the other ones have more than 2. So all I'm going to write here is terms with h's divided by h. These h's cancel, which is what we wanted. And then finally, we can see that when you plug 0 in for h, because this is what you're left with, right? Terms with h's in them. Once you plug that 0 in, they all vanish, and you're left with nx to the n minus 1. So in any case, that was just a little bonus, and it was a nice connection to the binomial theorem. But in any case, the power rule is a rule you're going to want to get good with, because it's going to move us away from using the limit definition involving the difference quotient, so that we can solve more interesting problems more efficiently.